Now the key to determining whether a basis is direct or indirect is called orientation. This is the process where we decide whether a given basis for a subspace is direct or indirect. So when you're dealing with a one-dimensional subspace, it's going to be spanned by a single basis vector. And you basically need to decide whether that basis is direct or indirect. And the easiest way is to decree, just say, this is going to be the direct basis. Anything pointing in an opposite direction is going to be the indirect basis. Another way is to choose any one form, which is non-zero on this single basis vector, and decree that this basis is a direct basis if the one form is positive, and it's indirect if the one form is negative. So if you use the one form that's dx1, the rule is simply this basis vector provides a direct basis if its first component is positive, right? If you compute the one form on this basis vector and returns a positive answer. Now if you're dealing with a two-dimensional subspace, it's going to be spanned by a pair of basis vectors, v1 and v2. And we want to look at the two oppositely directed unit vectors that are orthogonal to this subspace. So you could imagine v1 and v2 being like e1 and e2 in the plane, and then that oppositely directed unit vector would be positive e3 or negative e3. And you'd pick one, whichever one you wanted, and then you would see whether v1 cross v2 was pointing in the same direction as the one that you chose. An alternative to this, though, is to choose any two form that's non-zero when it acts on your two basis vectors v1 and v2, and just decree that the v's are a direct basis if the form returns a positive answer, and the v's are an indirect basis if the form returns a negative answer. And this approach actually works even when you're in R3. Picking a non-zero form that will never be zero when it acts on your three basis vectors. If it returns a positive answer all the time, then it will be a direct basis. If it returns a negative answer all the time, then it will be indirect. And it's actually this practice that we can generalize. Note that for any k-dimensional subspace of Rn, all we have to do is choose a k form that when it acts on our basis, it will never return zero, right? Because zero just is neither here nor there. And we'll decree that a basis is direct if that k form returns a positive number acting on our basis all the time, and a basis is indirect if it returns a negative number consistently on our basis vectors. We'll be doing several examples in class where we're given a form and given a basis and told, okay, is this basis a direct or indirect basis for this particular subspace given this form? Now how do we use this to orient a k-dimensional submanifold of Rn? At any point on the manifold, we can find a basis for the tangent space at that point. But the key is that we need a rule that will say whether a given basis is direct or indirect, and that rule has to be consistent over the entire manifold. When we move from one point to another, one of the vectors in a direct basis can't suddenly reverse direction. This might happen based on however we've parameterized that manifold. So that's what we're really trying to look to avoid. Let's look at some concrete examples. You'll do actual serious sort of computations in class, but just conversationally, hypothetically, let's look at a curve in R2. If we have a curve in R2, voila, a curve. And we're able to parameterize it, traveling from one part of the curve to the other. We just choose a unit tangent vector at one point on the curve and decree it to be a direct basis for the tangent space at that point. And then we can slide it along the curve to find a direct basis at other points. Similarly, for a surface in R3, just choose a unit normal vector at one point on the surface and say that a basis for the tangent space at that point is direct if the cross product of those two basis vectors is going to point in the direction of that normal vector. And then slide that normal vector along the surface to define a direct basis at other points. Like so. The same basis that you have found cannot suddenly generate an inward pointing normal vector when you take the cross product. If it switches direction, that means that you haven't successfully oriented the manifold. So what's the generalization? If you have a k-dimensional submanifold of Rn, you choose any k-form field for which it will return a non-zero answer when acting on your basis of the tangent space of this manifold, and decree that a basis is direct if it consistently returns a positive number, and it's indirect if it consistently returns a negative number. And for a manifold that's specified as a locus function, that should be a big F, I will change that in the notes, we can show actually in proof 22.2, it will show how to construct that desired form that will adequately test whether a basis is direct or indirect. Remember that any vector field can actually be used to define a two-form field, known as the flux form, by the following rule, where we compute the determinant of a 3x3 matrix, where the first column is the actual vector field, and the second column are the spanning vectors of a particular parallelogram anchored at some point on our surface. For a surface in R3, at each point of the surface, we can find a basis consisting of two vectors v1 and v2 that are in the tangent space, and there's a third vector that's orthogonal to the tangent space. One way to construct that is by just taking the cross product of those two vectors in the tangent space. Now, if you have a surface that is specified by an equation, f of x equals 0, we know that the tangent space is the kernel of df. So that if you take v1 and v2, those were the two vectors that were in the tangent space, df should map them to 0. And in this case, the matrix df consists of a single row of three partial derivatives, and its transpose is the gradient vector whose components are the three partial derivatives of that function f. And if the gradient vector of f is in the same direction as the cross product, that vector perpendicular to the tangent space, then the gradient of f dotted with v1 crossed with v2 is going to be positive. Equivalently, that also means that the determinant of the 3x3 matrix, where the first column is the gradient, the second column is v1, the third column is v2, is going to be positive. So this function, when we use this form, saying the determinant of first column gradients for second column v1, third column v2 is multilinear. It's an alternating function of the two basis vectors in the tangent space, and so it is a two-form field. So given f, we can construct a two-form field that orients the surface, and the construction is basically equivalent to the rule of check to see whether the cross product of your two tangent space basis vectors is in the same direction as the gradient vector of your surface. And this can be generalizable. Note that a manifold is specified by a vector-valued function f, where df is onto. The Jacobian matrix has n minus k rows, but you can still regard the transpose of the ith row as a normal vector. You can think about a curve in R3. At any point on the curve, there are two independent vectors perpendicular to the tangent space to the curve. Now, the general rule for constructing a form field that will successfully orient a manifold specified by a particular function is to make a gradient vector from each row of the Jacobian matrix. Then the function is the determinant of the following matrix. First through n minus kth column is going to be the gradient vectors from each row of the Jacobian. And then following that, we have the k basis vectors that are in the tangent space. Computing this determinant as a multilinear, alternating non-zero function of the basis vectors, and so its sign is a valid orientation for the manifold. Now, the tricky part of proving this construction is to show that the determinant can't be 0, and this is a generalization of the proof that in R2, two vectors that are orthogonal cannot be linearly dependent. We'll go through this in great detail, not just actually being given forms and saying whether a form orients a manifold, but actually figuring out how to find these particular form fields that are going to orient a manifold as well. And you'll be doing tons of examples as well as going through the proof of why this works. As always, if you have any questions, please don't hesitate to ask.